Hello everyone, my name is Ona de Givert and today I will be presenting to you our paper Scaling Low-Resource MT via Synthetic Data Generation with LLMs. This paper is the result of a collaboration of me and my colleagues at the University of Helsinki and also some colleagues at the University of Cambridge. In summary, we investigate the potential of LLM-generated synthetic data for improving low-resource MT. Let's dig into it. First of all, let's explain how we have created the synthetic data. We have chosen EuroParl, which is a corpus of document proceedings from the European Court that covers 21 languages and has rich metadata with document-level boundaries. Moreover, it's multi-way, meaning that it is aligned to multiple languages. What we do with EuroParl version 8 is we pass it through GPT-4o with this prompt, and then we translate it into 7 languages that are of special interest to us. These are Basque, Scottish Gaelic, Icelandic, Georgian, Macedonian, Somali, and Ukrainian. We have chosen these languages based on existing state-of-the-art model performance, linguistic diversity, and low resource coverage, as well as I have mentioned, practical interests, covering, for example, languages that are very present in Finland, where we are based. At the end, we have built multi-EuroParl, which consists of new synthetic EuroParl for the languages I have just mentioned, and also what we do is that we create 147 new language pairs via pivoting. So basically, because we make use of this multi-way nature of EuroParl, we can align all of the languages that we have to all the new ones. We also take the chance to introduce Syn Opus that you see there at the bottom, which is a new repository similar to its sibling Opus, but specifically for synthetic data. Once we have created the data, we want to have a look at it and see what's the quality. For that, we take 3 different evaluations. First of all, the 2 figures at the top are results of automatic metrics. We use Biclinar AI scores, which is a software that gives you a score between 0 and 100 of how probable it is that 2 sentences are a translation of each other. And then we also use Comet Kiwi scores, also a neural model that tells you the quality of the translations. If we look first at the automatic metrics, we can see that for Comet Kiwi, the scores are pretty high, not so much for Biclinar AI, and we can see this tendency in both graphs, where our data for Macedonian and Ukrainian is very high, followed by Icelandic and Basque, and finally, the lowest quality of our data comes from Scottish Gaelic, Georgian, and Somali, the least resource languages. Then if we move at the figure in the bottom, we also performed a human evaluation. You can find the annotation guidelines on the paper, and we only performed for 5 out of the 7 languages because we couldn't find annotators for the other languages. And here we can see a similar picture where Macedonian and Ukrainian get assigned very high scores with over 92% of the sentences that fall into the highest percentage bin, and then followed by Basque and Icelandic with a mixture of quality, and finally Georgian with over 40% of the sentences not being acceptable. So in general, we can conclude that our data is the best for Macedonian and Ukrainian, followed for Basque and Icelandic, and finally for Scottish Gaelic, Georgian, and Somali. And then we have a big, clear idea of that both automatic and human metrics confirm the quality of the generated data. Okay, now that we have created the data and have had a look at it, we want to use it. So what for that? We train a bunch of different models and do a lot of different experiments. First of all, we want to see what's out there, so we fine-tune some existing models as well as training our own. In the first row, we can see the synthetic baselines that we trained from scratch. These are transformer-based models that have 60 million parameters. Then we also evaluate out of the box Opus MT, EMNLP, and Llama, and fine-tune them as well. And you can see how the size keeps increasing. We can see that training from scratch is effective. Our synthetic baselines have quite high CHARF scores already. Then, fine-tuning boosts performance in all cases for OpusMT, EMNLP, and Llama. And we can see that in the case of Macedonian and Ukrainian, doesn't hold true for OpusMT because OpusMT models are highly multilingual, and in this case, they benefit from closely related languages. But in all other cases, we see an improvement. We can also see how bad quality does not mean useless. So we saw how in the previous step, our data for Scottish Gaelic, Georgian, and Somali was actually not the best, but then it has the biggest boosts in performance. So for example, fine-tuning OpusMT for Scottish Gaelic has an increase of 10 Charef scores, points, and so on. Then we can also see how general purpose LLMs struggle. If we look at Llama, out-of-the-box performance is really poor, and even though the fine-tuning helps immensely, we can see how it still lags behind the other encoder-decoder architectures. Finally, we have also evaluated GPT-4o so that we can compare our models, and we can say that we are competitive with GPT. On the one hand, we don't know what it has been trained on, so it may be contaminated, and on the other hand, our synthetic baselines, which are much more compact, have similar scores. Next, we want to see how our dataset compares with a real web crawl data, and for that we compare it with HPLT version 2. In this case, we use the same synthetic baselines, then we train also transformer base only with the HPLT data, and then we trained a third one combined with the HPLT and synthetic data. In this case, we only do it for the language pairs that overlap with our dataset, and we exclude Ukrainian because the HPLT dataset is much bigger, so it wouldn't be a fair comparison. We can see that if we look at synthetic and HPLT models, they have a comparable performance between a few Charef scores difference. And the best is that they are complementary when combined. So combining HPLT and synthetic dataset provides the biggest increase, which means that they are providing different enough information so that the model learned more. Finally, we can also see how combined beats transfer learning. So if we looked at the table before, we would see how in this case the HPLT and synthetic model beats EMNLP fine-tuned for Basque, Icelandic, and Macedonian, which was the highest scoring model that we had. Let's move on to the next experiment. We also wanted to see what is the effect of training data size. So what we do is that we train models in increasing batches of percentage of data. You can see at the bottom the percentage, and at the top the roughly percentage amount of sentences that we use. So we can see how overall there is an effective scaling of the use of the training data in the sense that all lines tend to go up. It is true though that gains decrease after 50-60% of the data has been used. So for example, if we look at English Basque, which is the line in color blue, we can see how there is quite a big jump from 10% to 60%, but then from 60 to 100%, the increases are much lower. So this tells us that basically if you want to work on synthetic data generation, you have to focus on data quality and diversity rather than on quantity only to see further gains. And now let's move on to our last experiment. As I have mentioned before, we have created this multi-Europarl via pivoting, where we have paired the new languages that we have with all the existing languages in Europarl. In this case, we are interested in Finnish-centric translation, and we trained models for Finnish Somali and Finnish Ukrainian, as these two languages are quite prominent in Finland. We do the same where we train synthetic baselines by basically training transformer-based models with our data, and then we evaluate out of the box OpusMT and LLP, and then we also fine-tune them with our data. For starters, we can see how our synthetic baselines are much weaker than before, around 40 Charef scores, but we can also prove that the pivoted data is useful. For example, for OpusMT, we see a very big jump for Finnish Somali and Somali Finnish translation. And also we see smaller increases for EMNLP in all the cases. Again, for Finnish Ukrainian and Ukrainian Finnish, we can see how the fine-tuning actually decreases a bit. This is because of the highly multilingual OpusMT models. So yeah, we have seen how to use our data. If you want to use it yourself, here you have the QR codes for our paper from arXiv. It will be soon in the ACL proceedings, the link to our dataset, and finally the link to our synthetic models, so you can use them yourself straight from Hugging Face. This project has been sponsored by HPLT and GreenLP, and we're looking forward to see you all in China. Thanks for listening and have a nice day.